All right. Yeah. So thanks for getting me up here. Very excited to be here in Cannes. And the funny bit is, I was pronouncing it as Cannes, but then I learned that it is Can. So cool. I'm Gajinder from Zeam, and we have been working on experimenting with the Beam protocol, which is which might be retermed as Lean protocol. So, I mean Beam or Lean. Whenever I refer, just interchangeably think that it's the same thing. All right. So, what I'm going to dig deep into is anatomy of lean proving. Welcome, Guillaume. And then we'll see that how proving is multidimensional and how at Zeam that we have run experiments to do multi-proving and what are learnings from that. And then basically we'll have some exciting announcement, juicy announcement relating to what we'll do. And before that, I want to get into what is the purpose of Zeam. So Zeam was conceived when Justin presented his vision for ZK Ethereum consensus. And our sole purpose is to basically demonstrate the workings of that ZK consensus. And we chose Zig for it because Zig is highly performant and Zig basically it's quite versatile to produce target runtimes that you can prove in ZK VMs. And our work is housed under Blockbill's organization in the repo Zeam, and then there you will also find other libraries and other functionality that we have built under the same organization, Blockblaze. And even though me and Guillaume are leading the team, but we have a very good set of contributors that are emerging and are contributing at various initiatives that we are doing for Beam and Zeam. All right, so again, let's go a little bit into what our mission is, because since the inception, we have been on a mission to build out POCs and demonstrate again how we can bring all the parts together in ZK consensus by integrating ZK VMs and also seeding the Zig community with the Zig ecosystem with the building blocks like SSZ, some P2P libs, maybe hash signatures at some point. And so that by the end of 2025, we can be Beam ready when we expect the specs to be released. And our mission is divided into two phases, and phase one and phase two. And we are 85% done on phase one, and we have pulled some goals from phase two into phase one as well. So we'll consider that we are 10% done over there. So now, as one of the outcomes of what we have been doing, so I'll dig deep into the anatomy of Zeam proving. So the core of proving is basically a guest program that is running inside a ZKVM, and then you have a client that interacts with it, and to produce the proof and then to verify the proof. So what exactly happens is that you have state and you have a block, and then you give it to, along with the guest program, you give it to the ZKVMs, which basically traces the computation and produce a proof that can be disseminated over the network. And then on the other side, the peer will have the same guest program and ZKVM, and they will verify it. And if you also transmit the state diff, they can also create a post state. So depending upon what the peer wants to do, it can basically just follow along the chain or just verify the chain, or even also build blocks. So now let's try to see how this entire proving thing fits in a slot. And now I have taken here a 3-second slot because that's what we are intending to do, 3-second or 4-second in the Beam/Lean protocol. And yesterday also, even in the Beam day, we had a good discussion about what slot length we should target. So in this particular slot, there are three main things that are going on. There is producer that creates the block and then executes the block so that it has a state root, which is just a commit to the block itself. That is what the final block is. And then you transmit that block, and then the peers will take that block, execute it. If it's valid, they will add it to their chain, and if it's their head, they will attest to it. And then their aggregators aggregating the signature, and then the signatures, aggregated signatures, are then added by the next block producer, so the cycle repeats. So if we add block proving to it, and if the proving takes, it's not real time, it takes a lot of time, then it's not really useful to the attesters or to anyone else who's trying to follow the chain and wants the correct head at any particular point. Because they would still need to, because the proof isn't available, they would still need to execute the block like all times. So you have to have that the producer is able to prove the block in real time. And if you look at how the blocks are disseminated, right? So here, for example, there are three stages to the block production. There are three things that are produced and transmitted. So it's like 3 delta, and each delta, if you assume that computation power is not an issue, you have good resources, and there is minimal time that is being spent over there. So most of the time will be spent upon disseminating the things that you have produced on each of the step. And if you look at Gossip Sub, the current average, or maybe 90% of the nodes, when they receive the message in 6 hops. And if you think that, okay, per hop you have about 100 millisecond, and then basically you have multiplied by 6. But we are trying to figure out how to disseminate faster, maybe in 3 hops, 2 hops, or 3 hops, depending upon whether we will be able to apply some grid topology to the network or not. But that is a question still far ahead. But let's assume that we are able to do in 3 hops. And then, so each delta is like 3 times 100 plus 200 times 200 milliseconds for just producing and doing the other chores that you need to do in that particular step. So you have 1.5 sec that is just spent just producing and disseminating the stuff. You don't really, so the time for proving is 3 seconds minus 1.5 seconds. But if you also have third parties, basically if you have non-enshrined proofs and there are other people who are taking the blocks and producing the proof and disseminating on the network, now that 3 delta now becomes 4 delta, so you actually have just 1 second to prove the block if you are trying to do it in real time. And basically this assumes that your block production and everything else is super fast. But if you have, for example, PBS in block production, there are multiple hops that are going over there. So it's a very, very tight schedule that we are talking about. So the real question is, can you do real-time straight transition proving of the block, which is basically maybe less than 1 second. So block is basically composed of 2 things in Ethereum. There is execution and there is consensus. And for consensus, definitely you can easily produce the proof in under 1 second, because it's quite a small computation that you need to prove. But for execution, there is a big question mark, because even if at the current gas prices, even if we are able to produce at the current gas limits, even if we are able to produce in proof in less than 1 second, we don't know, we are all trying to go for giga gas, so we don't know that might happen. So the right way to do it would be just-in-time state transition proving, which is basically, you have a delayed execution proving, right? So you don't prove that particular block in execution, but you prove the parent. So in delayed execution, you don't execute. So the peers are not meant to execute the execution part of the block at the same slot, but the parent should be executed and available so that you can verify that the state truth that is coming uh, in the execution header, you can match it with the parent one. So if you have that, if execution is delayed, so you have all this time that is available for proving the parent as well. So you don't execute and prove the current execution payload, but you execute and prove the parent. So that way you have now almost 3 seconds or whatever the slot duration would be available to produce the proof. And when you add various ZKVMs, third party producing the proofs, we get into the dimension of multiple kind of proofs that are being produced and disseminated into the network. And this is sort of what our emphasis has been in the last few months in Zeam, that how to do multi-proving. And then there are clients which will just pick one of the proofs, and they will basically have an integrated ZKVM, corresponding ZKVM, and they will just pick the corresponding proof, and then they will use it to validate the block. And the juicy stuff about this is that the peer doesn't need any EL connected to it, which gives us lean clients, because you get the proof for the entire block, both consensus and the parent execution payload, which is how things will happen in delayed execution. So with that, you will get lean clients. And even with APIs, things are not going to change that much. So the story is still going to remain the same. So let's now dig a little bit into proving diversity. So the basic building block of proving, or the basic component that you need for proving, is the guest program that you will run in ZKVM. And it is composed of three main things. One is instruction set, second is proof system, and third is runtime. So you have quite a large diversity in the instruction sets. So basically, we have RISC-V, we have MIPS already working and producing proofs on ETHProof's website. If you go, basically, you can see all the data. So we have 2 working instruction sets already, but then there are other instruction sets like EVM. Some ZKVMs are trying to just directly target EVM. And then there is Spectra, Miden, Cairo, Valida. But we don't have so much diversity on the proof systems, because there are 2 major proof systems over there, like Binias and Plunky 3, but most of the ZKVMs are working on Plunky 3 because Binias is not turning out to be that performant. Maybe things might change in future, but what is also happening is that all the ZKVMs to target, they are chasing the performance, and in that, they are also developing custom backends and proof systems like SP1 Hypercube. And then the third component is the runtimes, basically, which is state transition functions. And here, most of the ZKVMs might provide a default state transition function that might come with them. And here, the new players like Zeam will shine through, providing these runtimes that are integrated with various ZKVMs. So the first 2 components, basically, that is what your ZKVM is deciding. And then the third is a runtime paired with the ZKVM that your client might decide or might give you the option to configure for. And looking at ETHProofs, you can see that there are various ZKVMs which are trying a combination of instruction set that are there. And although I think in ETHProofs right now, 2 of them are integrated right now, but many others have planned to integrate with ETHProofs, and ETHProofs is sort of the place, it's sort of L to beat for these ZKVMs, and from that we can see how ready the ZKVMs are for the ecosystem. Okay, let's get further into multi-proving. So in Zeam, you have this Zeam multi-prover, and again, it takes a guest program. and the guest program is constituted by its runtime, which, for example, might be compiled to a target instruction set, RISC-V or whatever that is. For Zeam right now, it's RISC-V. And then you have some runtime glue and invocation glue that is very specific to the ZKVM that you are trying to prove with. And you have multiple such guest programs, which are basically compiled according to various ZKVMs that you have. So in Zeam, we have these multiple guest programs that are built and are available to the proving manager. And the proving manager will basically take the state. It takes a state, it takes a block, executed block, and it takes some proving ops that you can basically select which ZKVM and which guest program you want to prove with. Or you can just also do a multi-select. And here you can see our interface where you call into proof transition, which basically serializes this data to give it to ZKVM and calls the invocation glue, which is this. And then it goes into the runtime glue where you get the inputs from the ZKVM. And then you deserialize them and run the state transition and then commit to the outputs. And so in our work, we have successfully run this cycle with RISC-0. And we have also devoted quite a bit of effort into Powder, which is now deprecated. So that line is sort of now replaced by OpenVM because Powder is now OpenVM. And but now we are right now targeting ZISC as the next step. So coming to the juicy part of this talk. So with all the acceleration that has happened, so we have basically sort of updated our target to a more ambitious one. And our phase 2 mission is to have an EL integration, which is all right. I mean, it's okay. Everyone can do it. It's not really a big deal. But with delayed execution, that hasn't happened yet in the Ethereum ecosystem. So that is one of the EIPs that is being championed for Glamsterdam. But here we are saying that, okay, we'll go after it to do full block proving, as we have talked about in our talk, with a Zig invocable guest. And this will give us demonstration of a lean client where there is no EL. All right, thank you.
So do you have any question for our colleague?
Have you thought about proving DAG-based protocols?
Which protocols?
DAG-based, where you have a DAG of blocks and some of them are parallel. So it's not a sequence of blocks that fit into a single chain all the time.
So basically, I mean, what you're really saying is that what kind of state transition function that we are proving, right? But
No. I'm saying suppose you have blocks that are created concurrently and they're ordered later. You would need to assign the prover of each block before you know the total order. Have you thought about this direction at all?
We haven't thought about it because we are focused on what Ethereum path for that is. But essentially, even if that would be there, you would first prove each of the individual bundles, for example, and then you would prove the order, right? So at some point, you will have to order them up and prove the order as well. So if you have a recursive proof, I think that you will be able to solve that problem.
Another question? We have time for one more. All good? Okay.
All right, thank you.
Thank you, man.